there are a lot of questions in energy, because energy is going to be one of those common things you're going to see often on your test, along with the kinematics. Question 1 is actually kind of tricky. You got to be a little careful, and you have to be able to understand conservation of energy. So we know that GPE is equal to KE. They want us to find the kinetic energy, but we can't use the kinetic energy equation because kinetic energy is equal to 1/2 mass velocity squared. We don't know the velocity of these objects, but I do know that GPE is equal to mass times gravity times height. So I can figure out GPE, but if I figure out GPE and I can figure out the totals, I know that they're going to be equal to each other. So the first thing we need to do is figure out what we have. So we know that we have mass of the object, which is 1 kilogram. We have the distance, which is our height. Now, it says it's dropped at a height of from a 90-meter cliff. So this is going to be our total, which is going to be important. But it wants us to calculate the kinetic energy of the object after it has fallen 20 meters. Well, if it's fell 20 meters, that means it's at the maximum height of 70 meters high. So you're not even using the 20-meter number in the equation. You have to be able to say what height is the object at after it has fallen 20 meters. So we first need to figure out what the maximum height is after this object has fallen. So we're going to do GPE equal to the mass times gravity times the height, which is the total. And that's going to give us 900 joules. Okay? Now we want to figure out what it is at the 70. So GPE equals 1 kilogram, 9.8 times 70. That's going to be 700 joules. So if this is my maximum, and this is the GPE at the 700, when this is maximum, this is also equal to the total kinetic energy. Well, if this is how much GPE I have remaining, that means I have to subtract these two, so whatever's left over is going to be the kinetic energy. So I'm going to draw this real quick. So I have the cliff. This is 90 meters high. The object has fallen for a total of 20 meters. Let's say this is right here. Down. Which means that this is a total of 70 meters high. Up. So 70 plus 20, that's a total of 90. So at this point, my GPE is 900. GPE at the very bottom, at 0 meters, is going to be 0. Because we have no gravitational potential energy if we don't have any height. That means that kinetic energy at the bottom, right before it hits the ground, is going to be 900. So kinetic energy up here then would have to be 0. So if I know that the GPE here at 70 is 700 joules, then I know that the GPE up here is 900 joules. If I figure out the difference, whatever's left over is the kinetic energy remaining. So the kinetic energy is going to be 200 joules. So 900 minus 700. Okay. Question number 2, if the speed of a car is doubled, the kinetic energy of the car, so if I'm looking at kinetic energy, is 1/2 mv squared. So if we double the speed, because this is squared, that speed isn't going to be doubled, but quadrupled. equation. For number 3, we're going to go to number 4. As an object falls freely, the kinetic energy of the object is going to increase because your speed is increasing. For number 5, an object weighing 15 newtons is lifted from the ground at 0.22 meters. The increase in the object's gravitational potential energy is approximately. So GPE is equal to mass times gravity times height, which is 15 for our mass. Gravity is 9.8. And our height is 0.22. And that should give you 3.3 joules. Oh, I'm sorry. For this one, you're not putting 9.8. So, really quickly, and this is a common mistake that you can make. So, if I look at the equation, it says I have 15 newtons. So that's a force. And remember, that's the weight. So that's mass times gravity. So you already have mass and gravity already in there for the 15 newtons. So you don't put 9.8, but that's something that, is just an accident to put in there. And you need to make sure that you're really careful reading out and pretty much list everything that you have. So this is just 15 times 0.22, and that's where the 3.3 joules comes from. So really be careful with what you have because you may make a mistake, like I just did. Number 8, the work done in moving blocks across a rough surface and the energy gained by the block can both be measured in joules because it is energy, and energy is always measured in joules. Number 9, calculate the speed of the sled. So we have several questions here, which is 9 through 11. So the first thing we're going to do is calculate the speed of the sled with the 50 kilogram child. So let's write down what we had. 50 kilogram child, which is our mass, running at 6 meters per second. So that's our velocity. Onto a stationary 10 kilogram sled. So we have the second mass, which is 10 kilograms, on a level frictionless surface. Move that over. So question number 9 says, calculate the speed of the sled with the child after she jumps onto the sled. So we're looking for what is that speed going to be. So we have two things. We have our 50 kilogram and we have our masses. So if I'm looking at this looks a lot like a momentum problem, which it is, because I'm looking for that speed after she jumps onto the sled, which means I'm looking for a final velocity that they pretty much both are going to share. So mv and mv, or we're looking for the speed of the sled. So we have a mass and mass. So this is going to play into energy. Mass of the sled is 50, and the initial velocity was 6 meters per second, which equals the mass of both the girl and the sled. So instead of 50, the mass is 60 because you're adding these two together, because they are now 1. Times the final velocity, which is what we don't know. But we do know that they both will share. So 50 times 60, and we're pretty much going to take this 60, divide it on each side, and that gives you a final velocity of 5 meters per second. Question number 10. Calculate the kinetic energy of the sled with the child after she jumps onto the sled. So now we're calculating the kinetic energy. Well, KE equals 1/2 mass velocity squared. So KE is equal to 1/2. The mass given is both of them, so it's 60 times the velocity, which is 5 squared. So kinetic energy is equal to 750 joules. Now question 11 says, after a short time, the moving sled with a child aboard reaches a rough level surface that exerts a constant frictional force of 54 newtons on the sled. How much work must be done by friction to bring the sled with the child to a stop? So all you're given is the frictional force. But this is an energy thought question. If this is the total amount of energy that the sled has while it's moving at its maximum, the amount of work that's needed to stop it is the force times distance. Well, whatever that force times distance is has to equal the same amount of energy that it had at its maximum. Otherwise, it will never be able to stop. So what you have at your highest peak is what you're going to have to use in order to stop it. So that means your answer is 750 joules because energy is conserved. Okay? Alright, next we're going to do question, let's see, 19. No, just kidding. We're going to do question 22. So 22 says a 60 kilogram runner has 1,920 joules of kinetic energy. At what speed is she running? So again, kinetic energy equals 1/2 mass velocity squared. So the total energy given, 1,920 joules, which is equal to 1/2 the mass, which is given, which is 60 kilograms, times velocity squared. So we have 30 v squared is equal to 1,920. So we're going to divide each side by 30, and that's going to leave us with 64, which equals v squared. We're going to take the square root of each side to get rid of the square, and that gives us 8 meters per second equals the velocity. Question 24. If the direction of a moving car changes and its speed remains constant, which quantity must remain the same? So no matter what, because the speed is constant and the size of the mass of the car does not change, kinetic energy has to stay the same. Alright, we're going to do question 28. What is the total work done by the boy in pushing the wagon? So it gives you an example up here. We have a boy that pushes a wagon at a constant speed along a level sidewalk. The graph represents the relationship between the horizontal force and the distance of the wagon that's being moved. So what is the total work done? So remember, work is equal to the force times the distance. So the total amount of force that we have is 30 newtons, which is constant. 30 newtons of force is being applied over a distance of 4 meters in this case. And so that means that it is 120 joules. Okay, number 29. As the boy pushes the wagon, what happens to the wagon's energy? So if I look at my choices, it says gravitational potential energy increases. Well, this is an object on a horizontal surface that is a level surface on a sidewalk. That means it has no height. So there is no gravitational potential energy. So 1 and 2 are out. That leaves us with internal energy. So remember, internal energy is just energy because an item exists. It's not based on height. It's not based on compression. It's just there. So if, though, we're looking at that increasing energy is either increasing or if the energy is decreasing. Internal energy, as the boy pushes the wagon, that energy itself cannot decrease because that means you're gaining the amount of energy based on motion combined with it, because of the kinetic energy, which is also going to be considered internal energy, can't decrease because you're gaining it, which means that the internal energy is going to increase. Now, if you were slowing down, the internal energy would decrease. So internal energy is just another word for kinetic energy. So just make sure you keep that in mind. Alright, let's do question number 30. A 1 kilogram book resting on the ground is moved 1 meter at various angles relative to the horizontal. In which direction does the 1 meter displacement produce the greatest increase in the book's gravitational potential energy? So we're looking at pretty much any of these that are being pulled in that direction. If I pull any of these at any of these angles here, besides the 90, it's going to remain on the ground. If it remains on the ground, that means it does not have gravitational potential energy. If I pull it at 90 degrees, that means it's going to go straight up off the ground, which will increase gravitational potential energy because it has height. So that means your answer choice should be number 4. Okay, the next question we're going to do is 31. As shown in the diagram, we have a student which exerts a 600 Newton force on a rope to lift a 50 kilogram crate at a vertical distance of 3 meters. So my GPE is equal to whatever the boy is. We're comparing the two, the boy and the crate. So we have GPE is equal to 50 kilograms for the crate, which goes times our gravity, which is our 9.8, times the height that it travels, which is 3 meters. We're going to compare that to the GPE or by the boy, which is equal to the amount of work that he does, which is equal to force times distance. So the force he applies is 600 newtons, and the distance that is done is the same, which is 3. So this has a total of 1,470 joules. This has a total of 1,800 joules. So that means that the gravitational potential energy gained by the crate is 330 joules less, since this is the crate and this is the boy. So it's 330 joules less than what the boy had actually done. So you're comparing the two. The amount of energy, gravitational potential energy that's gained by the crate is going to be 1,470 compared to the boy's 1,800 joules of work that's done. Okay. Alright. Next, we're going to do the roller coaster on the next page, which is questions 34 through 36. So, a 250 kilogram car is initially at rest at point A on a roller coaster. The car carries a 75 kilogram passenger and is 20 meters above the ground at point A. Neglect friction. So for 34, we need to calculate the gravitational potential energy relative to the ground and the car and the passenger at point A. So GPE equal to mass, gravity, height. For the mass, you have to add the two masses of the objects together because they are together, which means they're all going to be 1. So 250 plus 75. So that's going to be our masses as added together. Times gravity, which is 9.8, times the height, which is 20 meters. So GPE is equal to 63,700 joules. Question 35. Calculate the speed of the car and the passenger at point B. So KE equals half mass half mass is still your 75 plus 250, and your velocity squared is what you're looking for, because kinetic energy at point B, because it's at the bottom, is going to be equivalent to whatever your GPE was at the top. So that means that this kinetic energy is 63,700 joules. So we're going to simplify that. 63,700 joules is equal to 162.5 V squared. Divide each side by 162.5, and that leaves you with 392, which is equal to V squared. To get rid of the square, we're going to take the square root of each one. So that leaves us with 19.8 meters per second for the velocity. Question 36 says, compare the total mechanical energy of the car and the passengers at point A, B, and C. Remember that mechanical energy is equal to the gravitational potential energy plus the kinetic energy. It's also equal to the elastic potential energy, but we are not calculating that here because the question says to neglect friction. If we're neglecting friction, then there is no elastic potential energy. So we're just adding the total energy up together, which is your actual total, and in that case we've already calculated that, which is 63,700 joules. So because of the law of conservation of energy, the mechanical energy for these two are going to be the same throughout the entire closed unit, which is the roller coaster. Question 44. We have... Actually, we're going to skip 44 because it's the same thing, finding the kinetic energy of the object. You should be able to do that by now. Same thing. Similar questions. They're pretty much repetitive. So, I mean, I would try some of these questions. They're pretty much the same as the roller coaster, and kind of see how you did. Same thing with this energy, gravitational energy versus vertical height. I would give those a try, and if you need to see any of those, just let me know, and I would help you out. The next one is, we're going to do the car one. It says that a wound spring provides the energy to propel a toy car across a level floor at time initial. The car is moving at a speed of v initial across the floor, and the spring is unwinding as shown below. At time equals t final, the spring has fully unwound and the car has coasted to a stop. So automatically, you should know there's a spring in the car, which is your elastic potential energy, but that's causing the velocity over time from our initial to final. Once the spring is totally released, we know that the kinetic energy has decreased to nothing by the time it goes to no velocity. Kinetic energy is at its greatest once the spring constant has totally unwound. And then it comes to a stop. So we know we're looking at kinetic energy here. So if we look at the statement, which one best of these describes the transformation? Gravitational potential energy at T initial is converted to the internal energy at T final. Remember, internal energy is the same as kinetic energy. So gravitational potential energy at T initial, first of all, doesn't have height. If it doesn't have height, there's no gravitational potential energy. Number two, elastic potential energy at T initial, which is the wound spring, is converted to kinetic energy at T final. Well, that's not true, because at T final, velocity is zero. If velocity is zero, there is no kinetic energy. So it can't be number two. Number three, both elastic potential energy and kinetic energy at Ti are converted into internal energy at Tf. So that means my kinetic energy and my elastic energy are converted into internal energy. So internal energy is the same as the kinetic energy, which is here in the car. But remember, internal energy can still exist if it's not in motion. But it's still that kinetic. So don't get that too confused. If an object exists, it's just it has internal energy because it has energy itself. If it's moving and it also is existing, then it has more internal energy. But once it stops, there is no more kinetic, there is no more potential energy, which means it's totally internal energy. So that would be the correct statement. Question number 3, both your potential energy and kinetic energy were converted into internal energy, which is the car just existing itself. Both kinetic energy and internal energy at TI are converted into elastic potential energy. That's not true because the entire spring has been unwound. So your answer choice should have been number 3. Okay. Alright, I think that's going to be it for energy. That pretty much covers mostly all of it. There is still a lot of information here. I think the most confusing one you might get used the internal energy. But remember, if an object exists, it has internal energy. You sitting here watching this, you have internal energy. If you increase that energy by increasing your height or moving in motion, you're going to increase the internal energy as well. So even if you're not moving, energy's still there no matter what. And I think that's it for now. There's going to be a lot of questions over energy, but it's really based and focused around GPE and KE. Make sure that you understand those two concepts, and you should be okay.